By welcoming everybody to our last colloquium of the fall semester. And Kristen, stay on, stay on. um, we're recording. I wanted Kristen to stay on because she's been doing a tremendous amount of work behind the scenes, arranging visits, arranging for the Zoom sessions to run smoothly, and I just want her to introduce everybody to her and make sure that um, she knows that she's appreciated. So thanks very much, Kristen, for all your work. Um,
Thanks.
and I will now just remind everybody about how the process here. Um, I um, I will be the one who's monitoring the raise hand function and the chat. Um, if you have any quick questions of clarification to raise during the talk, I'll keep an eye on it and get you in. If you have longer discussion type questions, please hold them until the question and answer period after the talk. Um, and our guest today is Carl Williams, who's the Deputy Director of the Physical Measurement Laboratory at National Institute for Standards and Technology. And I'm going to turn it over to Jung-Sang Kim for a proper introduction.
All right, well, thank you and welcome everybody. It's a great pleasure and honor to have Carl Williams give a physics colloquium today. Just a quick background, Carl is trained as a theoretical physicist in atomic physics. He graduated from Rice University in 1981 and received his PhD from University of Chicago in 1987. He has been working at NIST starting in 1998, and certainly has been a core member of pushing the quantum information and quantum sciences effort within NIST, and then of course way beyond. So he's a fellow of the American Physical Society and the American Association for the Advancement of Science. He's won various medals and awards for his contributions in both scientific contribution and also the impact he's had in our community. So he has left a lot of marks. One of the big ones from a scientific research point of view is he was instrumental in establishing the Joint Quantum Institute, which is a joint effort between the University of Maryland and NIST in Gaithersburg to create a joint institute for quantum sciences back in 2007, which currently, of course, is a huge success. Also, he's led and represented the internal effort at NIST for many years. And more recently, he's also served at the OSTP in the President's Office in 2008 through 2010, coordinating the strategy and the investment efforts around quantum information technology from within the government. And since then, he has been a big supporter of the quantum information research community in general. And he serves as the within the interagency effort to make sure that all the quantum information efforts are coordinated within the government. I'd like to conclude my introduction with my personal encounter with Carl. I was still a young researcher at Bell Labs in 2004 when Carl and a couple of other people from NIST visited us and discussed about the potential collaboration in quantum information, especially ion trap quantum computing. And up to that point, I had absolutely zero experience in that field. And after that meeting, we started a little internal study group within Bell Labs for about 6 months, thinking about learning what the field is and thinking about new ways that we can bring new technology to the field. And that June, I left Bell Labs and came to Duke and concluded that that was an exciting area. So I actually switched my career and started working on trapped ion quantum computing. Of course, when Duke hired me before that, they had no idea this is what I was going to do. So in that sense, Carl has been an inspiration, and then certainly the initial point for me to switch my career to get us to where we are. So in that sense, I'd like to thank Carl, and without further ado, introduce you to Carl.
Thank you, Jun-Sung. It's a pleasure to be there. Again, as some of you may know, I was supposed to be there roughly more than a year ago, and physically, and this is the third time. So the third time is charm in this case. So I'm going to start out by giving kind of a policy view about how science policy is formed in the U.S. But before I do that, I want to talk about how I define what is quantum information science, and I think it's important. I think it's also important to realize that, you know, the first hint of quantum information I will claim goes back probably to Richard Feynman. And if you've never read his story about Plenty of Room at the Bottom, which was an after dinner speech, you should go read it, because again, it kind of is there that you first get this hint. When we get to the very, very small world, say circuits of 7 atoms, we have a lot of new things that would happen that represent completely new opportunities for design. Atoms on a small scale behave like nothing on a large scale, so they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms down there, we are working with different laws, and we can expect to do different things. We can manufacture in different ways. We can use not just circuits, but some system involving the quantized energy levels or the interactions of quantized spins. I think this is remarkable that a man can see so far into the future, because the concept of quantum computing really goes to Peter Shor in 1994. So, you know, this is long before this comes out. And in fact, a lot of where quantum information evolves from was the limits on classical physical processing. And I point that out because reversible classical computing leads slowly into what becomes quantum computing and quantum information science. You know, I think it's important to say what it is and what it isn't. There's a lot you hear out there about what quantum information is. I like this definition. This comes from Bill Phillips, one of the Nobel Prize winners at NIST. Quantum information is a radical departure in information technology, more fundamentally different from current technology than a digital computer is from the abacus. The reason I like it is because it doesn't say anything that's inaccurate, and yet it tells you how phenomenally different this is. I think there's another way of looking at it, and that is that it's a convergence of two of the 20th century great revolutions. It is a convergence of quantum mechanics, which really comes from the end of the 19th century and the beginning of the 20th century, and information science, which comes out of physics and complexity theory, out of communication and complexity theory, and is really a mathematical formulation. It really wasn't based on anything physical at all. It is the realization that you can take these two things and merge them together, that you really end up with what I will call the second quantum revolution, or quantum information science. And so it is really transformative. It's going to be highly disruptive, and I will come back to that point as we go on through. So what is it? Quantum information science exploits unique quantum properties such as coherence, superposition, entanglement, and squeezing to acquire, transmit, and process information in ways that greatly exceed capabilities. And I will point out that NIST has programs across the whole region of this area. We've had a formal program since the year 2000. I sometimes tell people that in more of a lay audience that, you know, what quantum information science does is it exploits the strange pieces of quantum mechanics, the pieces that Einstein didn't like. And you know, if people don't fully comprehend how complex this is and everything else, I point out to them that Einstein spent more time trying to prove quantum mechanics incomplete than he did spend on the foundational principles that he contributed to. So again, this is really mind-boggling, and yet it really gives rise to great new capabilities. So what is it? Well, you know, it's still evolving. You can do quantum key distribution systems today, do short-range quantum communications. There are increasing quantum measurement systems out there, including chip-scale atomic clocks and other things. Quantum sensors are coming around. You want to do general purpose quantum computation or quantum networks, this is still a decade or more into the future. But I think that why it is so interesting is that much of what we will probably use this technology for, we have not even thought of. So I like to talk about quantum networks for relativistic geodesy. What is relativistic geodesy? Well, let's go study the breathing modes of the Earth. And the first one of those modes to ever actually be seen was only 2 or 3 years ago. And this technology actually has a sensitivity over a long baseline to, in principle, be able to see the breathing modes of the Earth and perhaps understand the pressure that builds up in the tectonic plates along the San Andreas Fault, so we could predict that earthquake 2 weeks early and get people out before that massive earthquake comes and would have killed millions. And then you can see over here on this far right, this little quantum games and toys. And I am sure if we can make it robust enough and we can fit it into our smartphones, we will see this come around. Why? I can build a game now that has 100 correlated events between the 100 players and ensure, because 2 to the 100 is a very large number, that the game never plays the same way again twice. And there's no cheating. So here is a billion-dollar market, multi-billion-dollar market, if we can put it into an iPhone and we can communicate and do things. So it is really the future. A lot of it is unknown because we don't fully comprehend everything we might be able to do. So I hope I've kind of given you a view of why we should care about this. And as a result, I want to talk a little bit about science policy and science funding in the United States. How do we make decisions about major efforts and everything else? Well, I want to start out with the first thing is, and within the U.S. government, there is no single science agency. Science agencies is spread among so many places. And I show you on the right of the slide some civilian and defense agencies that support science. It is really, science is spread among those agencies whose missions need it. And so it's mission driven, and yet we fund basic research across the whole arena in both areas. And usually the agencies decide where they're going to go and how they're going to evolve. But occasionally we run into areas where science, because the scientific issue becomes big enough that it crosses multiple agencies, and we need to figure out how to create a coherent policy so that we don't drop things and we do things well. And so I'm going to tell you a little bit about this. And so for complex and national level issues, the Office of Science and Technology Policy, which is part of the Executive Office of the President, basically is authorized to lead interagency efforts to develop, coordinate, and implement science policy. It's also within there that the President's Council of Advisors on Science and Technology, known as PCAST, also exists. This gives public information into the process as well. So I'm going to talk a little bit about this in the next slide. So for those of you who don't know about the Executive Office of the President, it is a massive operation. It occupies 2 or 3 buildings right down next to the White House, both the Eisenhower Executive Office building, which is just next door to it, as well as what some people I've heard call the Red White House, which is where OMB is, about a block away, and some other areas. But all of the offices of the President sit within those buildings and also within the West Wing, including the Office of Science and Technology Policy. So OSTP, it's part of the Executive Office of the President. The OSTP director is a member of what is called the National Science and Technology Council. This is the scientific council that's cabinet level for all issues across the government on science and technology policy. In the current administration, Kelvin Drogemeyer is the director of OSTP. In many administrations, but not in this administration, nor in the Bush Jr. administration, Kelvin is not the president's. He's a president's science advisor, but he's not an advisor to the president. He does not report to the president, and therefore he is not the science advisor to the president. He is the president's science advisor. Michael Kratsios, who I put up here in yellow, is the Chief Technology Officer of the United States. He is a deputy advisor to the president, so he actually reports to the president. He actually has more influence, and this was the same in the Bush administration. Typically, it is often the OSTP director that has political connections, but in this case, it's Michael Kratsios. NST is the interagency arm of OSTP, and underneath it, there's a bunch of committees that are populated by all the agencies that are part of doing science in the US. And so there's multiple committees, Committee on Science, Committee on Homeland Security, and a number of others. I point out these two because under the Committee of Science is the Subcommittee on Quantum Information Science. So we're going to come back to this in a minute because this one gets mandated into law, and we will talk about how that got mandated into law and its origin. There is a second committee on quantum that sits under the Committee on Homeland and National Security called the Subcommittee on Economic Security Implications in Quantum. And I am a co-chair of this committee. I am co-chair by designation of the NIST director because law says that the NIST director co-chairs this committee. He designates that position to me, and I sit in that position as a result for the NIST director, who is a political appointee. I also sit on the subcommittee as well, which deals with the national security implications around this field. So that's a little bit about how science policy gets made, and that science policy interfaces with the Office of Management Budget, which basically controls the budget process for the president. And so we can advocate for increased budgets in critical areas like quantum information science. Before I talk specifically about quantum information science and policy, I want to come back to quantum information science worldwide. And I like this and it's slightly dated now. It's a little over 3 years old, but there was a nice article in The Economist talking about the worldwide investment. And I want to point this out because there's some very interesting things here. Here's a country, Singapore, of only 10 million people. It spends the most money per capita of any country in the world on quantum. Netherlands also spends quite a bit of money per capita. So does Sweden. The United States is over here is quite big, 360 million. Look at Canada to our north, 100 million. We have 10 times the population of Canada. So the numbers don't tell you everything. You have to look at that broader perspective, how much per capita is spending. So there are a number of countries that have very big programs. Austria is another one that has a very big program relative to its size, as does Switzerland as well. There is a race not only to exploit the science, but to turn the science into technology. And China is spending a lot of money in this area. They've been making investments now for more than a decade. They started out back around 2008 or 9 with very large investments in quantum communications and quantum key distributions, and they now probably are the largest publisher of papers in quantum communications and quantum key distribution in the world. There are a lot of countries that have built satellite QKD efforts. There is no satellite QKD effort in the United States. There are plans for a entanglement-based experiment by NASA. The EU has just launched basically about 4 years ago a big new $1 billion flagship program around it. The UK has been spending money, created what was called the UK Quantum Network. And they had 4 hubs that were funded in 2014. They were refunded in 2019. Total of about $250 million going to those 4 hubs over a decade. The mission of the UK program is to make the UK a go-to place for the development and commercialization of quantum technology and a leading player in the global supply chain. So you can see a lot is going on worldwide. If you come back to the US, you can see lots of large companies are investing in this. And I will talk about the Quantum Economic Development Consortium in a little while. But there are companies all over the place investing both in quantum computing as well as in sensors and other technologies. And the number of startups is just tremendous, including one that is partially based here, I guess, at Duke with Jung-Sung Kim, INQ. So a lot of activity going on. You also are beginning to see consulting groups coming out and making market predictions. So I don't think this market prediction is wrong. We have separately done an evaluation and come up with similar numbers of $2 to $5 billion by 2024 globally was what both the consulting group predicted, and surpassing 450 billion annually in the coming decades. So this is going to be a very large industrial area. So why invest now? Well, clearly there are national security implications around this because of its roles on breaking public key infrastructure and cryptanalysis, that is breaking cryptography. And there are also many other potential economic benefits to this, from biomedical fields to, again, relativistic geodesy, which can save lives. And it is the frontiers of science, and I will come back to this over and over again. So we are at a tipping point, and other governments are investing in it, and it's important that we begin to develop the means to push this technology forward. So let me talk about how we got where we are today, and I'm going to take this from Shor's algorithm to National Quantum Initiative. Again, you know, it really is a merger of quantum mechanics and information theory. So the big names of the 20th century are all there, and there are Nobel Prize around quantum control, NMR, atomic clocks, Turing Awards for computation, and everything else. 1994, Peter Shor comes out with Shor's algorithm. This is probably the launch point for the beginning of US engagement seriously in this. Didn't mean that programs being supported at NSF and elsewhere beforehand, but Shor's algorithm really brings the government to the table. Why? Well, if you can build a quantum computer, you can break our cryptography. Oh, that's an issue both for national security and economic security standpoint. So every time you go to an HTTPS website, any secure website or anything else, you do a transaction on the internet or anything else, you're using public key infrastructure. And this is all gone when the quantum computer becomes available. So starting in 1994, the first workshop ever held on quantum computing and quantum communications, solely held, was held at NIST. We actually put this together shortly before Peter came out with his algorithms, but by the time he showed up, oh, there were these little people in suits coming down to us from nowhere. Why? Because in 1994, NSA stood for No Such Agency. It was classified, it did not truly exist, but NSA was there. They did manage to open their cryptographic museum after hours to allow us, including all of our foreigners, to go and visit their museum, which was behind the fence in 1994. That was a remarkable thing. By 1996, the Jasons had done a study on quantum computing. 1999, NSF holds its first workshop around this area. So beginning in the 1990s is when we began developing formal programs around QIS. And there are articles and things that you can go look at and see that were done. This is the Jason report and the report from NSF. And you see Charlie Bennett, again, IBM person, David DiVincenzo and others that were there. Dave Wine was also mentioned there. In 2000, DARPA creates a very large program called Quantum Information Science and Technology. That was a great program and we continue to build. In 2008, I went downtown to OSTP, and within a year, we had produced a federal vision for QIS. So this is the first vision document that comes out from the US government saying where we should go. And again, it's really a science-based vision document, but one of the problems we realized in 2008 and 9, and we made an effort to solve this problem, was that we were losing all of our computer scientists that were trained in quantum information. They were getting their degrees in the US and then immediately being exported because we weren't producing jobs for them. And we tried to fix that problem, working with NSF and everything else, and failed initially. By 2015 or 16, we had rectified the problem, but we failed initially on solving that problem, even though we threw money at it. You say you throw money at it, people will come. Well, they didn't. The computer science departments were not interested in quantum information theory at that point. In 2016, we published a second interagency document coming out of the NSTC on QIS, advancing QIS for national challenges and opportunities. And this is the beginning of where the NQI Act comes from. In fact, basically summer of 2016, as elections ramping up, I have discussion with a number of the professional societies, including those that were part of the National Photonics Initiative. And they're saying, what should they do? I said, well, it's an election year. You should come up with some policy documents. And that is, in fact, the origin of the NQI. And I'm going to come back to that in a minute. By 2018, the National Strategic Overview for QIS has been established. And that is basically where we are today, as well as the passage of the National Quantum Initiative Act in December of 2018, and two Defense Authorization Acts. So these are, again, some more of the documents that you can find on the web. I'm going to come back to the Bush administration. Again, I was told that the document I produced in that last year of the Bush administration, which was that QIS document, along with a number of other people, that was the fastest policy document that ever came out of the Bush administration. It only took 8 months to do. And I point out this, and I encourage you to go download. I'm not going to read it all, but Jack Marburger was a great science advisor. The interesting story was that I had written a glowing 5-page dear colleague letter for Jack. It went to the front office. The chief of staff wrote the standard three-paragraph letter for Jack that he wrote at the front of most of these documents. Jack tore up that letter and wrote a 7-page elegant document. If you go read it, it shows you that all the way back then, we understood the time was going to come where industry is going to move this field forward. It was absolutely aware of it, and you can see Jack Marburger had the insight to know that, and this was part of the reason I went down last year of the Bush administration. So let's talk about our current policy document. It takes a science-first approach. This is a little different from where the UK and the EU has gone. And we really are taking a science-first approach. We think that the science has to be solidified. In fact, industry thinks the science has to be solidified. We don't know all that big playing area and what the real applications are. We also understand we need to begin building the critical infrastructure and the supporting infrastructure necessary to build a quantum industry. But we see it as the early years. Again, in the summer of 2018, there was this White House summit, setting a new national strategy. And you can see Jake Taylor there. Jake, again, went down to the White House at my request. I recommended him to OSTP, and he was hired as the Associate Director for Quantum Information Science on detail from NIST, while he spent his first basically 2.5 years down at OSTP as well. So this was done. The closing remarks at this summit that was held in September was given by Lamar Smith. Lamar Smith is also one of the authors of the NQI Act. And in December of 2018, the NQI Act becomes law. So it shows you how this happens. What that act does is it says that the U.S. will set up a National Quantum Coordination Office. The interim director was Jake Taylor. It is now has passed on to Charlie Tahan since Jake left in June to come back to this, and currently on sabbatical up at Harvard. And it formally established and requires for the next decade the existence of the Subcommittee on Quantum Information Science. That is a requirement in law now, and so for the next 10 years, or actually 11 years, if you read the law carefully, that committee must exist. And it set up a National Quantum Initiative Advisory Committee, or FACA, Federal Advisory Committee Act, that has now been established by DOE and had its first meeting about a month ago. So I'm not going to go through this whole slide, but to see how you go from a policy document that came out at the end of 2016 to a law and everything else, there's a lot of activity going on. And I want to point out how important this is. Again, the origin of the NQI Act comes from the professional societies. And I am going to point out, this is important. NQI is the first time the professional societies in the physical sciences came together to create major legislation. The final legislation doesn't quite look like that draft law, but they help put it onto the plate. I am forbidden by law to advocate to Congress. I can tell the professional societies they should do what they are allowed to do by law. But it's important for scientists to engage with the professional societies and to engage with the broader thing. Science advocacy is important. Your congressman will like to hear from you. Speak to your representatives. They need to look at the big picture, not be parochial. QIS is going to be a major endeavor, and the best legislation should not be overly prescriptive. You want it to be flexible enough that we can adapt and move it in a way that is good. The NQI Act led to the establishment of a coordination office for the third time in history. The last one that really has an impact in physics is known as the National Nanotechnology Coordination Office, the NNCO, and that was established back around 2000. I would say one of the smart things was that you can see our coordination office disappears in 10 years. So it requires authorization for it to keep it. We naturally put a sunset clause in it. Congress can always extend that fairly simply, but getting rid of something that's been established in law is really, really hard. So let me talk about NIST and the National Quantum Initiative Act in industry. So, our program is both to extend our basic and applied research, to continue our workforce. We have two institutes that focus on this, and to expand collaborations. And it gave us also what's called other transactional authority. And I will come back to that because this is different from a grant or contract, and this is how we actually set up the consortium. It also required, not later than 1 year after the date of the enactment of this act, the director of NIST shall convene a consortium of stakeholders to identify the future measurement standards, cybersecurity, and other appropriate needs for supporting the development of a robust quantum information science and technology industry in the United States. And we have done that. We have set up what's called the Quantum Economic Development Consortium that is currently ran and managed by SRI International. I also have a report that's due on December 20th of this year, because it's the 2-year date of the enactment of the law. That report is going through process for being cleared, so we can send to Congress. So let me come back to the birth and the development of an industry and why this is important. 1947, the first transistor. Who ever thought it would lead to the integrated circuit and the millions and millions of chips that we have today? But that is the industry it takes to support this. And I don't expect you to read through all of it, but it is not just Intel. It is a massive undertaking. It is roughly 7 to 8% of the global economy. Every smartphone, everything has chips in it today. So it's massive. So what we wanted to do with the Quantum Economic Development Consortium is to build the supply chain for this future industry. Because by building that supply chain, I will also build component technology that will make the physics experiments far more efficient. Because people don't need to go build lasers like they did back 40 years ago. They can go buy them today. But we want to begin understanding what are the common component technologies that support this. So this is not just quantum 2.0. A lot of it is quantum 1.0. But the idea is to build that supporting infrastructure, because if we build it, then the big companies that are going to build the quantum computer will have the supply chain. So how many different companies contribute to a smartphone? Well, again, tens, hundreds. And it is building that industry that we want to do with the consortium. So to support in building that supporting industry, and to develop the workforce it needs, to understand what that workforce will look like. Industry had come to us and told us over time that they would like a couple master's courses so their system engineers could understand these quantum physicists. So we are beginning to try to understand from industry what they think their future needs are. And this is going to be evolving over the next decade, but the consortium can help us figure out with not one company telling us this, it is the whole infrastructure for supporting that industry that's telling us what they need. So again, a massive undertaking. I will point out, NIST had its first workshop with industry around quantum technologies in 2002. The next one was in 2007, 2012, 2014, 2015, 2016. So you can see an increasing engagement, but all the way back in 2002, Motorola, which no longer exists, Motorola, when they came to that workshop, said, we just spent 3 man-years evaluating this technology. It's not time for us to move. But they were already monitoring it all the way back then. So the QEDC is thriving. It has basically over 120 companies, national labs, universities, and professional societies that are members. More than 100 of these are companies. They've created a number of roadmaps and held a number of workshops, and they provide a lot of information that is beginning to be valuable to the U.S. government, because we're understanding where companies think the industry is going to go. And it's really important that we're not hearing from one company, but from a collective. NIST has basically put in place with the QEDC a $50 million other transactional authority agreement that has a maximum of $50 million over 5 years to help support building out this industry and to support R&D that would help begin to build that supply chain, to help build more efficient cryogenics, ones that don't take a 3-phase plug to get you to 100 millikelvin, but hopefully only 220, and other kinds of things. So we're really going to have to change how some of the technology is done if this is going to become efficient. So the cryogenic roadmap, in fact, had 5 action items. The one that we are currently working through the QEDC with to put out a request for proposals to the industry is on low size, weight, power, and cost cryocooler technology. This technology is probably only about 10 to 15% efficient at the moment. Highly inefficient because it's always been toys for physicists. So I come back to the policy options. While we take a science-first approach, we are deepening our engagement and beginning to try to understand that broader technology development that would help everyone, including building 100 gigahertz arbitrary waveform, 100-channel microwave technology. Again, wouldn't you like to have that in your lab to drive something, and other kinds of things? So what are the common technologies that we would use both in doing R&D in academia, but would also push the industry forward and eventually lead to the supply chain for this industry? So let me say a little bit about NIST. Again, we are the nation's measurement lab, and I point this out. We have facilities primarily in Gaithersburg, Maryland, and Boulder, Colorado. Again, we have 6 labs in our laboratory program. This is mostly what NIST does. We have a couple of external programs as well. The physical major lab is one of those. I want to point that out. Our quantum information science actually runs across many of our labs, including some of our technology labs, but not yet the engineering lab, which is really a systems lab. The goal of the PML is to set the definitive US standards for nearly every kind of measurement employed in commerce and research, and to be a world leader in the science of measurements. So you ask, what does that mean? Well, we realize the SI. The thing we realize best is time. We build the best atomic clocks in the world. We measure time to a part in 10 to the 18th. And you have to understand a lot of physics and have very good control of your quantum system to do that. We also realize the volt to a part 10 to the 10th using the Josephson effect. Again, Josephson technology is another one of those technologies that goes into quantum computing. We disseminate the volt over 21 orders of magnitude. We disseminate resistance over 21 orders of magnitude. The technology it takes to disseminate and provide that measurement infrastructure for the US is what my lab does. So basic research is part of it, and we have to push the basic research in order to improve measurements. We have 2 existing joint actually 3 existing joint institutes at 2 locations. We have the GILA at the University of Colorado, which has a lot of quantum information science, and we also have the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science at the University of Maryland. The JQI is predominantly with the Physics Department, and the Joint Quantum Center for Quantum Information is with the Computer Science Department. They're co-located and work very closely together. So I'm just going to skip through these slides fairly quickly. Let me just come back to the history of QIS at NIST and talk a little bit about that, and then show a few highlights. So we first become involved in quantum information probably in 1992 when Dave Wineland out in Boulder basically suggests an idea for spin squeezing for building improved clocks. And that project eventually gets funded the following year by the NIST director as a competence project, and basically is part of what leads to us having this workshop in 1994. It also leads to the situation where Ignacio Serrat and Peter Zoe proposed a quantum gate based on ion traps. And out of that competence program, Dave Wineland and Chris Monroe, then at NIST Boulder, implement the first quantum gate. So again, you can see Chris Monroe and his path out, eventually forming the collaboration with Jun Sung around ion trap quantum computing. So that's how we get involved. We actually formally established our program in 2000. This is how I get dragged deeper and deeper into this, and it's been a lot of fun. I also have to point out in 2012, Dave got his Nobel Prize for his research and board of QIS, and one of my pleasures was to get to go to Stockholm with Dave when he got his prize. So that was so much fun, I have to just say again. So it's been a lot of fun. I've talked about clocks a long time. We've been manipulating clocks for 70 years. The blue dots are our microwave frequency standards, our primary standards. Our primary standard is still NIST F2, it's a fountain clock. But the red dots are optical clocks. And you can see that the optical clocks are currently have better frequency uncertainty than the microwave standard. This will probably lead to another modification of the treaty of the meter in around 2024, 2026, when we redefine the second, because that process is underway. But again, this is one of the reasons we had such good things. I want to point this out because I want to show you some results from Dave Wineland from a decade ago. In 2010, you could take his aluminum ion clock, and this is what's shown on the left over here. Here's his aluminum ion clock. As you excite that aluminum ion clock that's sitting in that ion trap to the first level, the second level, the third level, the fourth level, you can begin to see that the clock ticks a little slower. Why? Well, that's just special relativity. Come over here to the right. They took the clock that was sitting there, jacked it up on hydraulic jacks, 30 centimeters, roughly a foot, and you can see the clock ticks in the opposite direction. Why? Well, it's in a different gravitational potential. That is general relativity impacting our clocks. Oh, all the way back then. I also will point out this clock has been running for a decade. This clock uses quantum logic in order to operate. So we've been using this technology already for a decade at NIST to build one of the world's best clocks. Talk about Josephson junctions. This is part of our superconducting quantum effort, but again, Josephson standards, we produce these inside NIST. In fact, roughly half of the world's voltage, traceable voltage systems have been built by NIST. We provide them to other NMIs. PTB in Germany provides roughly the other half. There are a few that are commercial, but we put 300,000 Josephson junctions on a chip because that allows us to build a 10-volt voltage chip. We've been doing this for years. The quantum Hall effect also defines resistance. So again, this shows you where some of those chips are. And again, it kind of gives you an idea of why we have this ability. Talking about very high-speed arbitrary waveform generations, we today can drive these things at above 100 all the way up to about 500 megahertz. We will probably create the highest speed arbitrary waveform synthesizer out of this technology. We've been exploring it for a while. This is an effort led by Sam Bands. One more thing about the kind of crazy things NIST has done. You know, people may think proving Ohm's law is hard. And I'm going to tell you it is damn hard. So we went to prove that V equals IR. How did we do that? Well, we used the Josephson effect. We used a single electron transistor, and we used the quantum Hall effect. And we basically closed this triangle all the way back at the end of the 20th century. And nobody has done better than we have done in proving that. Now, when we were done, we said nobody in their right mind should be doing this. The single electron transistors, counting electrons, oh man, what a pain. Oh, but we're back at building single electron transistors. So again, a very remarkable thing because again, we proved this at a part in a million all the way back in 1999. And sometime in the future, this technology will go into an instrument that was sitting on your table and will provide you traceable, highly accurate metrology for any electrical measurement you ever want. Because if I combine two of those together, I can basically scale the device. So this was positioned to do QIS in part because of our clocks and because of our stuff around the Josephson voltage systems. So we have a long history of manipulating quantum objects. We also, in the early 2000s, built the first gigahertz rate quantum key distribution system. And I was involved in that project. It was a lot of fun. How do you pull your photon in broad daylight out of midair at a gigahertz rate? And we were capable of producing all the way back in 2006 and 2007 over 4 megabits of key per second with such a system. That same technology has been used to build the sensors that are in the Atacama Cosmological Telescope. So again, it shows you the application of this to things that physicists care about. You want to look and see how many photons are in a pulse of light? Well, we can count photons these days, and we can tell you how many photons are in a light. Here's a mean number of 4. You can go look at the Poissonian distribution of what it should be, and you can see the trace on the left. Here's the same counting of 1,000. I was talking earlier today of how we basically now calibrate high-powered lasers up to hundreds of kilowatts, again, using some slightly different technology. But one day in the next decade, we will be able to run a photon scale from a single photon all the way up to a kilowatt uniformly. So we are also interested in taking and embedding this technology in instruments and things that can be put on a shop floor, whether for or perhaps even an iPhone. And so we've begun working on efforts to see how we put this technology into more compact forms. One of the first things that we did this in was a chip scale clock that we did with DARPA more than a decade ago and built the first chip scale atomic clock. And the benefit of this is that with many of these quantum measurements, they are self-calibrating and we can fit them to function. So if we can put them into small packages and make them robust enough, again, you know, what you would use on a manufacturing floor may be allowed to cost $100,000, but what you need to put in a car can't cost more than 30, 40, 50, maybe $100, depending on what it is. But we've been building all kinds of devices. One of the devices is this RF field sensor for using Rydberg atoms. This is basically going to rewrite how we measure electrical fields in the United States. This is a really amazing device. We have a number of patents on this and have been providing technology around it. We're also trying to compactify these Josephson junction arrays and other vacuum technologies. So I want to come back to clocks again because we're not done with clocks. Today out in Gila, in Juni's lab, we have clocks that are basically million atoms in a Fermi degenerate, all in the ground state of a lattice. And they tick together. you can compare the ticking on one side of the clock to the other, and if you tilt it ever so slightly, you can see the difference in the ticking because of the relativistic effects, the general relativistic effects. This may become the best tool in the future for looking at certain kinds of dark matter detection or detecting gravity waves. So we have been building an all-optical clock network out in our Boulder labs and comparing clocks between Gila and our Boulder, both through fiber and free space. We have actually made the most accurate measurements, relative measurements of 3 different transition frequencies of the 3 clocks that have ever been done. And we can actually begin to build an optical clock network that is more than 2 orders of magnitude beyond what you can do with microwaves and two-way time transfer. So this has been demonstrated out on Boulder labs. And you ask, why would you want to actually build this network? And I'm going to come to this in a minute. So we compared our aluminum clock, our aluminum ion clock, the ytterbium clock, and the strontium clock. And the strontium clock is what's in that Fermi degenerate gas in Gila. It is a really remarkable system. And we could compare those clocks to better than a part in 10 to the 17th. And therefore measure the relative frequencies better part to 10 to the 17th. That's better than we can currently measure time. The stability and the accuracy is different because our microwave standards are limited to about 2 parts in 10 to the 16th. We have lots of stuff on integrated nanophotonics that we're doing as well, including creating microcombs and other things that are important, coupling in single photon sources into them, creating smaller component devices for entangled photons and other things. We've demonstrated a super radiant laser consisting of, again, of strontium atoms. Again, really remarkable, highly stable, and this may be the future of how you provide stability, because at the moment to get stability for these clocks, you need a very large cavity to get rid of vibrations and other things and all. So we've done that kind of technology as well. We have efforts around that are supporting things like ion traps, compact stable lasers, MEMS mirrors, frequency combs, high collection efficiency optics, single photon detectors that are better than 99% quantum efficient. Oh, measuring that was a lot of fun, and I can tell you a story around that. We are working on efficient cryogenic systems, multi-channel microwave generators, material characterizations, very low noise, including beyond the so-called shot noise limit or the Heisenberg uncertainty limit amplifiers using this quantum technology as well. So we care about this technology because it provides improved clocks. We really care about clocks. That's one of the things we do really well at NIST. Clocks so good that they sense their environment. In fact, the reason I can do that relativistic geodesy is because within the next 10 years, our clocks will have no value on Earth because the tidal waves and the modes of the Earth and everything else are going to limit our clocks. The only place they're going to have any value is in space. But if you put them out in space at one of the Lagrange points, and you have long baseline interferometer, it creates a whole new way of doing high energy and particle physics. And there are several papers out on this, but it is an area that is really, really quite interesting. So it also may allow operation in extreme environments. In fact, the primary place that chip scale clocks go, they go down into drill holes for oil wells. Advanced applications require clocks. Space-based navigation, clock-based geodesy, precision timing, space-based dark matter searchers. And not all dark matter, is basically some of the lighter dark matter things that we would be good at detecting. So a giant telescope for gravity waves, dark matter, and high-res microscope. This may be a future instrument in space. I want to come back and I'm going to end with this last slide, a poetic circle of life, because there's a nice story about LIGO and Virgo, because when this was done and the data was collected of the two neutron stars colliding, there was a remarkable thing that came about, because when that data was reevaluated, what you found out was that one of the elements produced in the collision of those two neutron stars was strontium. And notice, we know a lot about strontium because we built some of our best clocks from strontium atoms, and we could detect the strontium that was created in telescopes looking at those neutron star mergers. It's a wonderful story. We are witnessing the second quantum revolution, and this revolution, where it's going, we don't know, but it will use the weird properties of quantum mechanics to do all kinds of new things. And so I end with a slide, again, going back to Richard Feynman. Here he is, 1981. And if you make a simulation nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So thank you. I really appreciate your time.
Thanks very much, Carl, for a very stimulating talk. Yeah, it seems like you have to juggle a lot of balls as a director of NIST. It's impressive that you can keep track of everything there. Our tradition is to open the floor first to graduate students or postdocs for questions before the faculty jump in. So is there anybody who would like to ask a question? Use the raise hand feature if you'd like. I think our yeah. Okay, our graduate students seem to be a bit shy this afternoon. So let's open the floor to anybody. And let me mention also that I want to make sure that the attendees from UNC feel welcome here also. We've been running a joint Duke UNC Colloquium series this fall, and it's been great to work with Reiko Henning and Joaquin Droot. So I appreciate their efforts and the attendance of anybody from UNC. So the floor is open for questions from anybody now. Henry Everett.
Hey, Henry.
Hey, Carl. Good to see you. Appreciate the talk. It's been a while. I'm glad to hear what you've been up to lately. I have a couple of questions, but I'll just ask one of them for now. Back to your discussion about policy and how policy is made. And you made the comment that the scientific societies played an important role in the legislation that went forward and the creation of the policy that motivated that, which I think is terrific. I have a question about other factors that influence the policy making. And in particular, from within the DoD, it's never as much about the capabilities we're offering as it is about the perceived threat or gap that we might be missing out on if we don't keep going. So a lot of the motivation that we've seen within the DoD anyway over the last few years in quantum has been motivated by investments by the EU, by the UK, by the Chinese. And I'm curious to what extent the perceived threat to national security influences the policies that you were involved with.
So again, I think probably a lot of the interest, again, I actually was testified before the House Science, Space and Technology Committee in the fall of 2018. That was shortly after the Chinese launched their QKD satellite. And I think that also brought a lot of attention to the floor that the Chinese were moving that rapidly. I think that has played a role. I think there was a lot of discussion. There have been numerous bills, both coming out of the defense committees, at the HPSC, Senate Armed Services Committee, and others around quantum as well. I think as most of these congressmen and their staff do their work, they came to the realization that it remained largely scientific, so it needed to be very broad-based. So it got driven by the civilian agencies. And this just has to do with which committees control who's. There are authorizing committees and appropriation committees, and the civilian agencies have one set of committees, and the DOD and the IC have others. So it ended up realizing that if we were going to push this, the civilian agencies needed to increase their programs. And so that forced that. DOD has come back in and put some focuses on it. There have been other bills around. So I think both are playing a role. I think what is most important is that the government sees that this has both economic and national security implications. And so it needed to be a whole of government approach.
Okay, yeah, thanks for that, Carl. A follow-up question related to that. For us, a lot of our investment strategy has been about developing the tools rather than the quantum in the box, but the things that make the box practical, you know, the lasers, the integrated photonics, the detectors, all that. I'm curious to what extent the recommendation was to invest in those tools over the quantumness in the box itself.
So within the industry, the view is that we should not be picking winners and losers. So on the industrial side, the question is how do I build the supporting infrastructure so I can guarantee that the large system integrator that's going to win is going to win? And the answer is, you know, you typically end up with that system integration where there is sufficient supporting infrastructure. So it was viewed that if we did that, and at the same time, it allows the system integrators, the IBMs, the Intels, the others to move their programs faster. Because if they don't have to go build, so look, I visited a lot of these places. You walk in, you see Rigetti's microwave control electronics. You see IBM's microwave code. Everybody has built their own. Why? Because they can't go out and buy 100-channel microwave things. And so we need that. If you could go out and buy it, they would go out and buy it. Now, the reality is if you have a company who can produce a 100-channel microwave arbitrary waveform generator, they can probably do 1 million. And so that same company will then become the supply chain for that quantum computing company, because they will come back and say, here's what I'm doing. Build me my control system for this system. So the view is that you take that staged approach because you move the R&D faster, yet I'm not picking winners and losers. All I'm doing is supporting the broader industry that's going to be needed to make them successful. And so that was kind of the approach. I hope that kind of answers the question. Within the government, of course, we still fund everything. The basic research it's done at the universities. Yeah, go build me a 100-qubit quantum device.
Hey, Carl.
Hey, Ken.
I with you am always talking about how this quantum logic clock is proof that quantum information is already paid off in some sense. I'm just curious, like, what your second example would be.
What my second example would be. You have a second example?
So my second example is actually the use of NV diamonds in biosensors.
Oh, yeah.
People always knew about color centers, but they didn't have the control until they tried to turn them into quantum devices.
Yeah, I think that's probably true. And again, that technology goes back to manipulating spins and NMR and the Neil Gershwin quantum computing approach with NMR, which everybody probably finally proved was, well, yeah, up to a certain number, and that's it. Yeah, I think that's a good second. I think you can see several things coming down. I think that actually the first applications from a commercial standpoint will be on the support, what I would call the supporting technology. I mean, I think the use of single photon detectors, which I need, same way I need to be able to detect spin or anything else. I mean, I can't do quantum processing if I can't detect. And I think those we're seeing a number of places where those are coming in. In fact, the Atacama could be an example of that same technology being used to do basic physics because we can build the best detectors in the world.
Yeah, thanks.
Jung-Sang.
Okay, I have a quick question. So, you know, the quantum information, as you indicated, for the first maybe couple of decades was mostly R&D funded through the government activities, and you know, it's really taking a very different turn in the last 5 years or so. So, what do you think is the right kind of model for government and industry to collaborate to make things more effective and find successes, but also not losing sight of opportunities that are kind of hidden and not visible?
So again, if you will look at a lot of the calls around the new centers, but the DOE wanted industrial investment, the NSF wanted industry engagement. I think it's very important. One of the things the U.S. has never done well on, and we've tried to figure out how to do this, and it becomes more and more important as the world has become flatter and more competitive, is we don't do good on transitioning scientific concepts into technology. I mean, this happens kind of arbitrarily in the U.S., so so-called Valley of Death problem. And of course, you were at Bell Labs, and the last place that really did a great job on doing this was some of the stuff you did at Bell Labs with the Lambda router. I think it is essential that there be more interaction. I think the Consortium also provides a venue in which pre-competitive research can be done, and we can help lift the boats. So tell me what the common needs are, what the common goals are, what the common things are that would make R&D faster, make your life easier, make you more likely to succeed. And since I'm not picking any one to win, I'm picking all to win. I haven't violating any competition rules. So I think there's a lot that can be done around it. Industry wants to engage. They would like to have interns, graduate interns, come spend a summer with me. A number of places have programs around this, and the QEDC can help people who, if they're interested in doing that. So I think there's a lot to be done. I think there's a lot we can learn from each other. I think that the world isn't the same as it was, and we want to have to figure out how to remain competitive in a much more competitive world. I'm going to come back to industry. Industry drives this in some ways. If industry doesn't think that it's worth making an investment, putting some of their own money into it, then it's just the government funding R&D in industry. Industry has to see a path out the other end. And yet, you know, you can see talks where some of the big companies come back. I've seen several of these talks where how much are they going to invest before they turn a profit? And the quantum computing companies, some of them have basically, they claim they're going to spend $2 billion before they break even. That's a lot of money. You know, I think there's a place for us to work together and support each other. And if you have any ideas on it, I'd love to hear. You're on the PCAP, you're on the NQIAC, the National Quantum Initiative Advisory Committee, and so you know you should bring these things to there and tell us what we should be doing that we aren't doing already.
Absolutely. All right, look forward to it. Thank you.
Rico, did you have a question?
Yeah, I had a quick question. This is actually something that you had brought up earlier. So you said that there's, you had listed these 5 topics for R&D, and one of them was related to making cheaper refrigerators and figuring out ways. Because right now, of course, one of the, if you want to build the superconducting types of qubits, this is substantial startup costs for a small group involving buying a dilution refrigerator. So I was just wondering if you had any more comments about that and what the status on that is.
So that is a project that we're just beginning, and put out through the QEDC. The view is we have several concepts for doing this, and we would then work with industry to create that new infrastructure. The idea is initially to increase the energy efficiency roughly by something on the order of a factor 2 to 3, because we think that's an easy win without pushing things too far. And that can end up in two different kinds of devices. It could end up with a dilution refrigerator that can hold 2 or 3 times as many qubits, or it could end up in a dilution refrigerator that is a little more energy efficient, quicker to cool down, less wall power because of the way it works. So I mean, you only have that design trade-off, and the companies get to decide ultimately what their market is. We don't tell people where they should go. We just try to provide that. And the reality is what most people don't realize is this technology came from regular refrigerators. In fact, that pump is just the pumping of what was originally the pump on a regular refrigerator, and by chopping it, they could drive the thing a little farther and harder than they could, and it's evolved very little since the original technology, surprisingly.
Okay. Thank you.
If I may, I'll just ask one question, kind of about the scope of the envisioned initiatives in the following sense. All of the examples that we're talking about so far are essentially based on research conducted in physics departments and electrical engineering departments. And I'm curious whether whether there are contributions coming from a little farther afield. Chemistry is not that far away, but even say biophysics, people studying electron transfer in biomolecules, how broad a scope falls under this quantum initiative umbrella?
So NIH, and if it hadn't been for COVID, I believe NIH was going to launch a small program around quantum and bio. There'd been a lot of discussions and everything else, and COVID just overtook that effort. I will point out that one of the groups that the QEDC has been interacting with is called Quantum Pharma. And this is a group of pharmaceutical companies that have come together looking at how this technology may affect them. And there's two things here. And one of these goes back to chemistry kind of applications, quantum chemistry. And again, you have an expert in-house who can probably tell you more about this. Ken Brown can tell you a little bit about some of the quantum chemistry stuff. I know he's been at some of these meetings and discussions. But in the last 2 or 3 years, the efficiency of the quantum algorithms for doing quantum chemistry have improved by multiple orders of magnitude. And of course, it was always known possible, but until you start actually exploring it. And so those algorithms are going to get rewritten and redone in how they actually do them once a general purpose quantum computer is available. And in fact, what was remarkable is early on, one of the first real calculations done on a quantum computer was to do the Born-Oppenheimer model of H2. Why? Because it only takes a couple qubits. And yet they could do this to arbitrary precision. And you're just going through, yes, I know. I solved that problem when I was taking quantum physics. And you could do it mathematically. You don't need a computer. But the fact that 2 qubits was all you needed was kind of amazing. So I think that was one. The other has to do with the imaging side. Because again, a lot of the best imaging technology we can develop, especially for in vivo imaging in the visible. And we know how to put chromophores into drugs and other things that will be targeted. Collecting the light because you can't just turn up laser power and get more things if it's in vivo. That's called cooking your host. So again, having very sensitive detectors, and we actually have done an experiment. We took one of our detectors to Lausanne, Switzerland, and worked with a group there to actually watch the neurons firing in a mouse brain. and the fact that they had put in green pigments so we could see green light coming out and everything else, and we could basically map the neurons in the mouse brain. So that kind of technology and applications probably has a big space as well. So I think the use case area is just growing. They're trying to understand what might happen and where to go. So I think you're going to see more of it. I think the computer science departments now are fully aboard, along with the electrical engineering ones. The computer science, I mean, and you're talking about, so there are things like, and some mathematics departments too. So there's things around quantum random number generation. There's efforts around quantum algorithms, including ones that are not are what I will call quantum resistance. That is, you have to understand quantum algorithms if you're going to replace our public key infrastructure with an algorithm that isn't susceptible to a quantum attack or being broken. And in fact, NIST has a very major effort underway to basically come up with new public key infrastructure, hopefully by 2022 is our goal, to have that in place. That its competition is ongoing and has involved an international landscape.
Well, seeing no other hands raised and realizing the lateness of the hour, let's officially wrap up. We'll stay on for another few minutes if people want to hang around for a smaller conversation. But thanks very much, Carl, for spending the afternoon with us and for the very informative talk.
Thank you. My pleasure.
Yeah, this is one of the really frustrating things about Zoom lectures, is that you can't hear people clapping or get any real feeling of closure. But thanks very much.